Swayam Prabha. Digital India. Educated India.
We are going to continue our discussion of algorithms in randomized linear algebra. We have already talked about two problems. One is how to approximate matrix vector product. Then we went into matrix product. We recognized that matrix product can be done in one of three ways: inner product ways, as linear combinations of the columns of A by elements of the different columns of B, or as outer product, rank 1 outer product matrices of columns of A and the corresponding rows of B. So, we have to so the whole idea is we have to induce a randomized structure. To that end, I have to have a random variable or a random vector or a random matrix. We gave an example of a random variable. We gave an example of a random vector using matrix vector product. We gave an example of random matrices. Now, we are going to talk about the third problem, low rank approximation for A. We have already seen the importance of low rank approximation, because if A as a m by n matrix is a large matrix, either tall or broad, where the number of columns and the rows differ by a large amount, in such cases the matrix has singular values decreasing very fast. We do know from PCA analysis that the intrinsic rank of the matrix, even though the actual rank may be full, the number of eigenvalues which are small and close to 0 but positive may be large. In such cases, we should be able to concentrate only on those eigenmodes corresponding to the largest subset of singular values, let us say k. Using such modes, we should be able to approximate, we should be able to find a k rank approximation to A, and such a k rank approximation is technically called sketch of A. Sometime in mathematics we say, when you do not give too much space, we will say in a paper, for lack of space we are going to give only a sketch of the proof. We are not going to give all the details of the proof. The details of the proof are left to the reader to fill out. So, sketch means to give the major pathways in the thought process without giving too much details about every one of the computations in here. So, the word sketch is used in mathematical proofs. Yeah, a painter tried to sketch a human being, and so the word sketch is a good intrinsically represent a good approximation to something that we are interested in finding, conveying. So, the low rank approximation of A is called the sketch of A, where the columns and rows of A are picked in individual trial based on the importance distribution, and this importance distribution is based on the squared length of the columns and rows. Such a choice generally gives you a good sketch. So, here understand please, I have until now we either sampled the column or the columns of A and the rows of B. Now, we are going to also sample the columns of A and the rows of B. I am sorry, columns of A and the rows of A, because there is no B. I am simply interested in developing a sketch for the matrix A. So, let A be an M by M matrix. Let A be an M by M matrix. Pick S columns of A to form a matrix M by S based on the length of the square of columns of A. So, please understand LS column A refers to a distribution where the ith column is going to be picked proportional to the energy that is inherent in the ith column, and the energy is measured by the square of the length of the that column vector. So, I am going to pick S columns from that sampling distribution, important sampling distribution based on the column length. Likewise, I am going to pick simultaneously R rows from A using square length row distribution. So, LS row means what? I am going to define the distribution based on the energy in the rows. LS column means what? I am going to pick the column based on the energy in the column, and I am going to define a matrix R S by M. Now, please understand, C consists of the columns of A, R consists of the rows of A. So, I am selecting the rows and columns of A itself. Now, using C and R, so what is C? C is a submatrix coming from choice of columns. R is another submatrix coming from the choice of rows. Now, I am going to represent a new type of decomposition. Using C and R, I am going to express A is equal to CUR. The matrix C we found out in step 1, matrix R we found out in step 2. Now, our job is to be able to compute U such that the product CUR is approximately A, is a good approximation to A, and our job is to be able to compute how to quantify U such that this product matrix CUR would be a good sketch for the matrix A. I hope you understand the problem. You may think of using SVD to get a good sketch. Please understand, sketch can be obtained in several ways. If you have SVD, A is equal to U lambda V transpose. So, I can pick any number of eigenvalues. I should say this is the eigenvectors in our notation is lambda to the power half, just to be consistent with the previous notations. So, lambda to the power half is the singular values of A, which are the square root of the eigenvalues of the smaller of the two Gramian. So, using U lambda to the power half V transpose as we expressed in our empirical orthogonal functions, we can select only k eigenmodes or singular modes to be able to express. So, that will give you a good approximation, optimal approximation. So, that is one way. So, it is not that we do not know how to compute it, but the challenge is that computing SVD, first I need to compute the Gramian, that takes time, that involves matrix multiplication. Second, I have to compute solve all and we have to solve the eigenvalue problem. We have to compute all the eigenvalues and eigenvectors of the smaller of the two Gramian. You find U, you find lambda, you find V, and take the square root matrix lambda to the power half and express A is equal to U lambda V transpose. Then you pick a beta in some range between 0 to 1. Then you find a k such that the total variance explained, you can think of it as a total variance explained is at least 1 minus beta. So, using such an argument, we can already find a sketch. So, besides SVD, the columns of U and the rows of V are not directly, okay, look at this, this is another criticism for SVD. So, this looks like CUR, there are 3 factors, U playing the role of C, lambda to the power half playing the role of U, and V transpose playing the role of R. But what is the difference? In the case of CUR decomposition, the columns of C and the rows of R are directly picked out of A. However, the columns of U and the rows of V transpose are computed as a result of SVD, and we cannot directly relate the columns of U and the rows of V transpose to the columns and rows of A. So, that is what is being said. Besides, in SVD, columns of U and the rows of V are not directly from A, but are linear combinations of the columns and rows. In here, but SVD, despite its cost, it is the best approximation one can find. CUR is not optimal in the same sense as SVD is optimal. So, you can see that trade off here. CUR essentially picks the rows and columns of A, where SVD is indirectly related to A through linear combinations of the rows and columns. So, that is the difference between what we plan to do and what we have already done. So, the whole question now reduces to how to use how to choose U, Please remember A is m by n. So, I am now going to talk about an intuition right now, in an intuitive idea using which we can derive the good algorithm. Please remember A is equal to A times I. So, I can sample A columns, S columns of A and get the matrix CMS. Get the matrix C, which is of size M cross S. Let W be a matrix corresponding to the S rows of I, which is scaled as in matrix product. So, what is that I am now trying to do? In order to get a sketch, I am going to fall back on an old algorithm for doing matrix product. In the matrix product, we already have defined a sampling distribution, important sampling distribution, that takes into account the norms of the columns of A and the rows of B. Using such a distribution, I could pick S columns of A and build a matrix C, and W rows the matrix W, which consists of S rows of I, scaled in the way that we have introduced. You remember that we did that in the case of matrix product. So, A is equal to AI, A is equal to C times W. Now, we can fall back on the result from matrix. So, from 6, where we have defined the bounds on the matrix approximation, matrix product approximation. This is A times I, the product of A with I, which is simply A. CW is obtained by using the algorithm for matrix product, the square of the norm of that. Since C is picked with under a random distribution, C is a random variable, W is also a random variable. So, I am going to talk about the expected value of the square of the norm, and we already know the expected value of the square of the norm is upper bounded by the product of the Fourier, the Frobenius norm divided by S, the number of samples. The Frobenius norm of I, the Frobenius norm of W is I is essentially n. I is a n by n full rank matrix, and in this case the Frobenius norm of this quantity is equal to n. So, this whole thing reduces to n over f times the Frobenius norm of A. Since we need n to be greater than s to be greater than n, this is not a viable choice, but the idea stands. Please understand, n is the size, and I would like this to be as small as possible, and for that I need s to be larger than n, and after all that is not viable. Why? S is the number of rows of I, n is the maximum number of rows. So, yes, the number of rows I need to pick cannot be larger than the maximum. So, that is not viable. So, even though this idea is not viable, but it provides a pathway to the thought process. So, and I am going to modify this idea. So, what is that we need to do? I need to get a better surrogate for I, and that is what we are going to do. So, if the framework is good, the choice of I provides you a thought process. So, if instead of I, if I can choose some other matrix to play the role of I, but not equal to I may succeed in finding what I want, and that is what the modification is all about. So, let us consider C m by s matrix or R by n matrix. So, to recapitulate, I picked S columns of A and R rows of A to build two matrices C and R, and this must be n, that is right. The S columns, there are only totally n columns. So, S must be less than n, and the number of rows is less than m, the m rows and n columns. Now, I am assuming my R is a full rank matrix, and is quite likely to be a full rank. Why? They are corresponding to the large columns and rows with a large energy. So, I am picking a subset of rows with large energy. That means the lengths need not be the same. So, I am assuming they will be linearly independent. In such case, all will be full rank. If R is full rank, then R transpose R is an SPD matrix. Please understand, R is R by n, and R transpose R is a smaller matrix, is an R by R matrix, is an SPD matrix. I can compute its generalized inverse, which is, please, this is R transpose RR, R transpose times RR transpose inverse. This is the Moore-Penrose inverse, and this is the projection matrix that comes out of R. Please understand, I am trying to compute the generalized inverse of R cross capital R, which is R rows and n columns. So, RR transpose is SPD, R plus is given by this. R is less than n, I think R is less than n, therefore, this is a broad matrix, and I am going to consider the Moore-Penrose inverse. R P is the projection matrix induced by R, which is the n by n matrix. Recall, P acts as an identity on the row space of R. Hey, that is an important property of the projection matrix. That is a key idea. You remember, I had used A times I is identity. So, I am trying to find a surrogate for I, where I will not have the problems that I faced when I used I. So, the surrogate for I is P. What is P? P P is the projection matrix onto the space spanned by the selected rows of R. So, just to be able to give an idea, if R is 1 1, R transpose is 2, R plus is 1/2 1 1, and projection matrix in here is given by this matrix, which is 1/2 of 1 1 1 1. So, the row space of R is Y, which is R transpose A, which is P of Y, which now can be written as the projection times Y, which is R transpose A, R transpose inverse can get cancelled. So, this becomes R transpose A Y. So, what does it mean? Y is equal to, implies P Y is equal to Y, and Y is R transpose A means what? Is the linear combinations of the columns of the rows of R. It can be thought of Y is the linear combinations of the columns of R transpose. Columns of R transpose are the rows of R. Therefore, Y lies in the row space of R. So, this is a verification that PH acts as an identity matrix on the row space of R. So, we can replace I in our previous analysis by P. So, instead of AI, I am now going to consider AP. I am now going to substitute for the value of P, which is R transpose R, R transpose inverse R. Now, look at that, there is an R, this is the A. I am going to identify this part to be U. I am now going to pick the columns of A as I have done, which is C. So, this equality is exact, this equality is approximate. So, I am going to replace A by C, R by R, and the intermediate term, which naturally comes as U. And what is U? U is R transpose R, R transpose inverse. So, this is one way to obtain the sketch. Now, look at this now. This is a beautiful idea. I want to elaborate this a little bit more. So, what did I do? You pick C, you got the C. You pick R, you got an R. From R, you compute P. P is expressible in terms of R as R transpose R transpose inverse R. So, I have identified R. So, the remaining thing is called U, and U is essentially R transpose R, R transpose inverse, and what is this? This is the generalized inverse of R. So, this is the generalized inverse of R. So, what is U? U is a coupling matrix. So, I select a subset of columns, I select a subset of rows of R, I need to be able to couple them. U couples them in such a way that CUR now provides a very good sketch, very good approximation. And what is the quality of the approximation? The quality of the approximation is given by the inequality 6, which again comes from the matrix product. So, AP minus CUR is the error in the approximation expected, and CR are picked randomly. Therefore, there is an element of randomness in the error. So, expected value, the square of the error, square of the norm of the error. We do know the 2 norm is less than the Frobenius norm. That is a general inequality that comes from the relation to norms. So, which is very important in here. Given any matrix, its 2 norm is less than or equal to Frobenius norm. So, Frobenius norm is what we have, and we have an inequality that relates the Frobenius norm as we have seen earlier, and that is equal to the product of the Frobenius norm of A and P, product of the squares of the Frobenius norm of A and P divided by S. The Frobenius norm of P is R, where the Frobenius norm of P is equal to R, and we have already talked about it, but I want you to argue why. And where did we do that? We talked about the rank of the projection matrix when we talked about least square modeling. So now I want you to go back to the definition of the Frobenius norm. Square of the Frobenius norm is essentially equal to trace of AA transpose. So if I apply that rule to the Frobenius square of the Frobenius norm of P is equal to trace of P times P transpose is a trace of P times P transpose, but P is an orthogonal projection matrix. P is equal to P transpose, it is symmetric, and P is also equal to P square, which is idempotent. Therefore, trace of P transpose is the trace of P, and that is the result that brings you to this point. Now, I am going to substitute for trace of, I am going to substitute the expression for P. I am answering Y, that is the answer I am providing, R transpose inverse R. Now, we know trace of ABC is equal to trace of BCA is equal to trace of ABC. So, using this circular rule, I can now say this trace is equal to that, the product of that is equal to IR, and that is equal to R. Therefore, the Frobenius norm, the square of the Frobenius norm of the projection matrix is R by S. So, by combining all these results, A minus CUR is A minus AP plus AP minus CUR. So, what is that I am trying to do? I am going to add and subtract a particular term, that is a usual mathematical trick. So, I am trying to express this as a sum of two matrices. So, the norm by triangle inequality, the norm of this is less than the two norms, the sum of the two norms of these two terms, sum of the two norms of these two terms. Now, recall, so this inequality is essentially from triangle inequality for matrix norms. Please understand, triangle inequality is one of the important properties of norms, whether the norm of a vector, norm of a matrix, or norm of any quantity. For something to be a norm, that is one of the conditions to be satisfied. Now, recall, if x is less than or equal to y plus c, x square must be less than or equal to y plus z whole square. Y plus c whole square is y square plus y 2yz plus c square, and you can verify this is less than 2 times y square plus z square, 2 times z plus y square plus z square. That implies 0 is less than y square minus 2yz plus c square. This is y minus z whole square. So, by applying this argument to this, please understand, this is a scalar, this is a scalar, this is a scalar. You can think of this as x, you can think of this as y, you can think of this as z. So, what is that we have shown? If x is less than or equal to y plus z, x square is less than 2 times y square plus z square. So, that is the inequality I am interested in. We are trying to connect this. We are going to apply this inequality to this relation, and that essentially gives you the 2 norm of the error in replacing A by CUR is less than 2 times the square of the 2 norm of A minus AP minus 2 times AP minus CUR square. So, these are all squares. So, now you can see from here I can infer this by doing this little bit of an exercise using scalars. So, with that now we have shown that we can get a sketch without doing much of work. So, let us talk about this now in summary. I can find a sketch using SVD, but that is expensive. Not only is it expensive, but also the matrix U lambda to the power half V, they are not directly related to the columns of A and columns of rows of A, they are simply linear combinations of the columns of A and the rows of A. So, I lose the identity of the rows and columns when I go the SVD way. So, besides more time, I am not able to relate the columns of U to the columns of A directly, the rows of V transpose to the rows of A directly. That is the criticism of the SVD approach, but it is optimal. So, we wanted to have an alternate idea to get a sketch. We developed the notion of what is called CUR decomposition. This CUR decomposition in this case was derived as a special case of the matrix product, randomized algorithm for a matrix product. Instead of replacing I by B in the product AB, B by I identity matrix, I replaced it by the projection matrix induced by the matrix R, which consists of R column, R rows of the matrix A. So, if I picked S columns of A and R rows of A, the column matrix is called C, the row matrix is called R. I compute the generalized inverse, I compute the projection matrix. If you look at the expression for the projection matrix, I have C, I have R, somebody in between the coupling matrix. The coupling matrix is simply the generalized inverse of the matrix R. So, by nicely coupling this way, I can express A by an approximation CUR, and CUR has the required rank. So, that is the basic idea. With this, we finish our first introduction to large scale matrices. Thank you.